every single video is posted. For this particular session, I'll post it as soon as WebEx has a video, which I think likely to be this evening. We'll, as I said, skip this part. We'll do this at the end because I kind of want to make sure we go through the review first. Because if you have any questions related to any of these topics, we can address. So for the review, essentially what I want this class to be is it's going to be driven by you. I'm going to try to provide a big picture. And if you have any questions from the big picture, let me know. Right? Ask the question is you have the floor. So basically over here, the first thing that we learn in this class is for all the whole program in CS you learned so far, everything is related to the software. You always talk about how you program things, what's the algorithm, how you convert the algorithm to a program. In reality, after you have the program, which is a good, like, significant chunk of the steps that produce the desired output, right? The next little thing that you have to do is to basically convert that program into binary. And from that binary, make sure that the computer can run something. So the first thing we learn here is from your program. Let's say you have a program. And let's say you have a, say, Java program. What happened after this? After you say, hey, I'm running this program. What's the first thing after you have the program? What's the first thing you have to do? After you finish running the, I guess, writing the program, say in IntelliJ, right? What's the button that you have to click to move on from the phase of having the code to, yes, compile? Basically, you compile your code. After you compile the code, what do you get? You get this, the binary, right? This is the task of the compiler, so we're gonna skip what the compiler is actually doing. They actually have a lot of optimization. They learn what you do in the program, and they try to create a binary that do exact same thing that you program, but faster. Then from the binary, right? It basically, if you look at the, this is your system. I mean, not system, but your computer, right? Let's say this part is your hard drive, right? The binary is now stored somewhere in the hard drive, right? It's a file. Basically, it's a file you can run. Let's say this file is it's called test. What happened if you do this /test? What happened? What will happen to this file inside your system? It moves itself. Well, not that it moves itself. Basically, the OS, the runtime. Let me be a little bit more specific here. In fact, this is basically kind of like a task tool, right? The OS say, hey, someone want to run this thing, right? Someone want to run this thing. And then let's say you want to schedule this task and say, let's run it right now. This is what will happen. Your binary move on to here into, this is your DRAM or the memory. They are the same thing. Right? This thing get moved to your memory, right? How can I tell where is the first line of my code that I need to run? How can I tell that? the program counter. Right? So now you have the program. What else that your program might have? The data, right? The data is something like you initialize the array. You initialize the array. The same thing will go here. The data would get copied at a different region of your memory, right? This is where your data is, right? And based on what you write in the program, they are going to access the data. Right? Any question about this process on what happened when you start compiling the program and run it? Or any question here? All right, so assume that you have no question. If you have any questions, just feel free to type in. I'm gonna come back to any slide we have so far. Notice we have a slide number as well, so you can say, hey, can you go back to slide X? And I'm going to go back to that slide and talk about what happened. All right, so let's assume that we have our program here. Okay, program. And we have the PC right here. This is instruction one, instruction two, instruction n. Okay. If you zoom this in, right, as you told me earlier, the program is converted to a binary, right, which is basically a bunch of ones and zeros. That's my instruction. How can I tell that it is doing what? What does it supposed to do? This is basically one of the core thing in assignment one. So how can I tell what does this line do? You look at the opcode. Basically, you look at this bit pattern, right? It will tell you opcode and then operands. And then basically these provide you information on what to do with that line. Is this an add? Is this a load? Is this a branch? Right? Any questions so far? Now that we convert uh, your program into instruction for the hardware. So basically you would then refer to the ISA specification, right? That tells you, okay, if you see this pattern, this is what it means. If you see this pattern, this is what that means. The next thing I want you to be aware is there are multiple ISAs. It's ARM, right? MIPS, whatever you have in the lab, right? Those are another different ISA. I can also create my own ISA. The in-class exercise 5 is my dummy ISA that I use for the purpose of the class for that exercise. Right? You know, so take a look at risk 5. So what are some of the trade-offs that we discussed in class related to the ISA? Anyone want to tell me what are the trade-offs that we discussed in class? Why should I look into using the Intel x86 ISA, which actually right now kind of owned by AMD? So you might have noticed, right? Sometimes you have the 64-bit ISA, 32-bit ISA, even 16 or 8-bit ISA. Okay? What could have been the trade-off for different word lengths that you see here? What are the different trade-offs? You can specify more operations. You can basically embed, right? Embed more information if you have more bits. What are the downside of having 64 bits versus 8 bits? Storage, yeah, obviously is one of them. The another one is energy. Take more space, take more power. Exactly. So these different trade-off based on different ISA. You come up with the hardware to service the software, right? We are we are there to run the program. So we treat the program like a king and we service that program. If you know what program you're running, then you build the hardware specific for those programs. That way you can conserve space, give better power efficiency, and everything is about efficiency. Everything is also about performance and power, right? These trade-offs are important both on the ISA and the micro architecture. What else? Variable length versus fixed length. So what are the trade-offs between these two things? Why should I want a variable length? Why should I want a fixed? This is for the whole instruction, actually. Your instruction can take like Intel processor, for example. Your instruction can take 96 bits. What might, okay, let me put it this way. Which one is more flexible? So let's do a table with different trade-offs. Okay? Uh, Variable length is more flexible because you can adapt, right? If you don't need a lot of instructions, it will be small. If you want to somehow support more instructions, it's going to get bigger. That's fine because it's a variable length. As long as I know how many bits I need to fetch, I'm good. So this is more flexible. Which one is simpler? A fixed length is going to be simpler, right? Which one is more power efficient? It's actually unclear. Depending on how long is that and also how you design the actual instruction, you can't tell. Actually, you cannot tell. If you want to tell which one consume more power, basically you need to, the best way to do it is to actually run the program on different ISA. Sometimes the shorter length ISA can ended up consume more power because you ended up running so many instructions. Let's say, okay, how about this? Everyone noticed, right? I can actually create a multiply from an add, right? I can use a bunch of adder or I can use a bunch of add instructions to perform a multiply. So that's true, right? What if I say my ISA has no multiply and your workload just to matrix multiply? What can happen there? Is it going to be efficient or is that going to be inefficient? Code explosion, yeah, something like that. Basically, you ended up with the assembly code that is huge, right? Basically, your assembly code will be really long because you can do a multiply. Something that could have taken one line of assembly code now take multiple lines. What if I have a ISA that can support initializing arrays to zero? Right? That will actually allow your code to be a lot more efficient. Then the problem is you need to actually build the hardware to support that particular instruction. So the hardware can be more complicated. What is the difference between ISA versus the microarchitecture? Can someone tell me what's the difference between the two? ISA is not a translator, it's more like a specification of the hardware. It tells the programmer that our hardware supports these things. Microarchitecture is basically the implementation of those support. Basic ISA would claim, I can do this, I can do that, I can also do those things. Microarchitecture is the guy who actually needs to do all those things, right? So let me actually say, if you have the 32-bit program counter, is that a property of the ISA or the microarchitecture? The exactly 32-bit program counter. Is that the ISA or is that specified inside the microarchitecture? It's actually ISA, right? You don't the ISA tell it's 32-bit. So the programmer knows, okay, it's 32 bits. How about number of register files? Number of register, somehow I cannot write English word in the rec file. That's also the ISA. It would tell you, okay, x86 has EAX, EBX, all those things. It's specified by the ISA. How about the pipeline? Number of pipeline stages. Is that a property of the ISA or the microarchitecture? It's microarchitecture, yeah. Because you don't tell the programmer, okay, this is a 32 stages pipeline. They don't care. They just want to run their program, right? Another way to think about it is, from the programmer point of view, do I care about this? Or, yes. ISA is what's visible to the programmer. Microarchitecture are the hidden things that we put in as a way to implement the hardware, to make it faster, to make it more energy efficient. Right? How about the branch breaker? Is that the ISA or microarchitecture? Yes, it's microarchitecture. How about what else? I have a good thing. I have a good example here. Number of hardware threads. Is that the ISA or microarchitecture? Yes, because you know, right? You say you buy an Intel processor, you know, okay, how many threads are there for the hardware. Hardware thread is different from software thread. We'll go into that detail after we talk about memory hierarchy. It's really different. If you talk to system people and you refer to the word thread, you need to be specific. It's not a hardware thread or a software thread. It's different things. How about the size of the cache? So the hardware thread is like the management of hardware thread. How about the size of the cache? Is that the ISA or micro architecture? So this is actually microarchitecture because it's built to fake, not to fake, but basically to make your load and store faster. From the programmer point of view, you thought that you are loading something from main memory, just the way we implement the hardware. We fake it such that your load that's supposed to go to the memory go to this side really fast. All right. So the next thing that I want you to be aware about things we covered is how do we measure performance? The reason why I want to talk about this is probably closely related to, let's say you're done with this class and like I hate hardware. This is something that I hope. Yes. Yeah. Sure. I hope you are aware when you want to make a program faster. So what are the So one of you already told me what are the metrics. What is the IPC and what is the CPI? What does it stand for? Instruction per cycle. Okay, so let's say I have a CPU that can put out at maximum of 4 instructions per cycle, and I have a GPU that can put out a maximum of 100. Oops, sorry, 100 instruction per cycle. This is the CPU instruction. This is the GPU instruction. Who is faster? Which one is faster? So this is actually a trick question. You can't tell. The reason why we cannot tell is actually this. So we haven't gone into the way GPU run things work yet. It is let's say they run the same algorithm, right? You have the algorithm you want to run, and you have these two options. GPU and the CPU is different. I just tell you the maximum you can get. I'm just telling you the maximum that you can get. In reality, right? In reality, the way you compile the algorithm for a CPU and GPU, there are many things that can happen. You might end up running 4 operations per cycle here, and then only 1 operation per cycle over here. And if you design something that's supposed to run on the GPU, and especially if you don't rely on things like PyTorch or TensorFlow, those APIs that kind of automatically map, right, your code to the GPU, then there's a chance that you write your code in a way that is super unfriendly toward the GPU, and you learn why. Basically, you learn about the GPU toward the end of this semester. I will be really specific on why GPU is really good and why GPU can be really bad. I'll try to put, yes, that's one factor. How parallelizable is your code? If your code can be parallelizable, it's likely that you will fast on the GPU. Otherwise, it will suck. That's the reason why the GPU has not been used to run, say, Microsoft Windows, Microsoft Word, Chrome. There are good reasons for that. Okay? How many of you seen the apps by NVIDIA where they have like a paintball gun painting something on there? Let me show you this. I'm not sure how many of you seen this. This one. So you seen the video? Can you see the video? All right. So this is the content of the video. They basically, hey, we can like this is how the GPU works. It's claimed by NVIDIA. So you can kind of like have this super paralyzed like kite that paint the paintball gun, and when you fire it off, it's gonna become like a picture in one instant. Right? Fast forward. All right, stop it chatting because I'm muting this. Right here, I think is where the thing would. Alright, this is what they claim. This is what the GPU can do. You see the thing? All right, so let me switch back to the slide straight. In a GPU, that's what they claim. In reality, it only applies with a really, really strict guideline, right? You can't always get that performance. So if you know how each hardware works, you can then look at the application or the program that you want to run, and you know exactly what should you buy to get the most out of your program. Also, you can also tell yourself that, hey, maybe I want to rewrite the program to make it faster. How about the wall clock time? What is the wall clock time? Can someone tell me what does it mean when I say I look at wall clock time and I report performance? It's not time per cycle, but it's a unit of time as we know it. Basically, if I say this program run in finish in 5 seconds, it means that yeah, I look at a clock and it takes 5 seconds to finish the program. This generally is another good metric. It's similar to what we call execution time. The reason why execution time is almost always really important is this is the metric you want to aim for. This is the metric that we want to aim for. We just don't know sometimes how to measure execution time in the long term for the whole program. So we use IPC and CPI as a way to convey the same thing. There are a lot of details going into how to scientifically measure performance. Let me address this question a little bit later. Because if you want to measure the performance, there are different methods that you need to go for each program, for each way you have set up, such that you can fairly compare the performance. Measurement of the waiting time. So that's a great question. Basically, the question is like, that's another metric that you've seen before, right? It's called measurement of the waiting time. Measurement of the waiting time is actually closely tied to what we call the queuing theory. Queuing theory is what the name suggests. It has to do with how we can make sense about how long you will have to queue up things. Why are these important? Queuing time is both important in computer science and business. How many of you have to wait forever to get checked out in a supermarket? How many of you run into that, some instance of that at some point in life? I think we all have been in that situation, right? So you might have noticed a lot of supermarket has a special line for people who buy only a few items, right? Those are designed based on queuing theory. The queuing theory would have a mathematical modeling behind, okay, if I know these employees or like if I know human can check out at these many items per second, how should I organize the lines for the queue such that the wait time is on average smaller? Another important metric or instead of the average wait time, how long is the guy who has to wait the longest has to actually stay there in the line to get checked out. It's not the CPU time. This is time as in seconds, right? It depends on what you want to justify as that unit of time. Different application in the sense of like supermarket versus a highway versus your computer, right? The way you justify what time you are going to use is different. In a lot of cases, it's actually seconds. It's a wall clock time, right? How long, if I send this packet over the internet, how long do I have to wait until I get the reply back? Should I make a special line? Should I make any special treatment? Right? For example, in emergency room, right? So I think it's a really great analogy. In an emergency room, when you go in there at night, right? There's only one queue, but different patients have different priority. The patient that's likely to die first will have the highest priority in the ER, right? Because that kind of like follow the human logic, right? This process of basically having the person with the most priority get service first, basically this is called promotion. Basically, you have new patient coming in, you just have a cardiac arrest. Yeah, everyone should go treat that person, otherwise he will die, right? So that's the process of promotion. We do that in computer science as well. Let's say you have a request, right, from different program, and one of the program is the program that handle the OS. If you don't service this request within 1 second, the computer will crash. That particular request is more important than another request that just say, okay, I want to print something. I send a packet to the printer. I mean, I can wait like 10 more seconds. I don't care. I don't care. So hopefully that answers your questions about the wait time. Okay, and sorry I go a really sidetrack here. I think measuring performance is one important aspect of the multiple topic essentially in computer science. It applies to system, it's applied to the program, it's applied to the scheduler, it's applied to the hardware, it's applied to many things. And this is where math come into it. So if you like statistics, if you like probability, and you like math, I definitely recommend you to look into this area called queuing theory because it are not just applied to computer science, you can apply this to business as well. It's really one of the seek after area in multiple type of jobs. Anyway, now that I get super sidetracked, let's come back to the lecture. What is a single cycle architecture? What does it mean? What does single cycle architecture mean? Uh, right now, sequential execution is tied to von Neumann model. So I forgot to mention this actually. What is von Neumann? What does it mean? You run code sequentially based on the order of instruction. How about data flow? Is basically run code, right? Run your program based on data, the data's availability. Uh, what is single cycle architecture? This means that you execute all instructions using one cycle. So my question is, what determine your clock frequency? What is the factor that impacts your clock frequency of single cycle architecture. If you say every single instruction will take one cycle, so let's say I have this as a unit of time, right? You have instruction one, instruction two, instruction three, and instruction four. Let's say you only support four instructions. Instruction one take this much time, two take this much, three take this much, and four take this much. If you say every instruction should take one cycle, what would determine your clock frequency? How fast you can clock your CPU? Which of these four instructions will be the bottleneck that determine your clock frequency? One, two, three, or four? Why four? Yes, it's instruction three. This is the slowest instruction, right? So basically the slowest instruction determine how fast you can clock your CPU. If you clock faster than this, there's no way you can finish instruction three on time. You just finish the clock too soon. The write back phase of that instruction, the last arrow line is just the axis for time. The write back phase have not finished writing back yet, and you basically clock it. So you can't finish write back. You can't support that. How about multi-cycle architecture? What's the benefit? So what's the benefit of the multi-cycle architecture? It's not about performing many instructions at the same time. That's pipelining. Multi-cycle architecture allows different instructions to take different number of cycles. So let's go back to the same example. Right? Instruction one, instruction two, instruction three, and instruction four. And instruction one take this long. And I just said, okay, I'm gonna clock it right. Yes, exactly. It's kind of like when add take one cycle and multiply take four cycles. I'm gonna clock it so that the clock cycle is this long, right? So this would take one cycle. This thing would take two cycles. This thing would take one, two, three, four, five cycles. And this instruction four would take four cycles. It means that you don't have to wait for instruction three anymore. If you're running just instruction one, it only takes one cycle. One cycle here is faster than one cycle back in the earlier example, right? You now subdivide that time into 5 chunks and only take one chunk to finish instruction one. So that's the benefit of multi-cycle architecture. Then we talk about pipelining, which is what exactly one of you said. Let's say you can run, right? You have fetch, decode, execute, memory, and write back. Let's say you have instruction one right here. This can be running instruction two, and this is instruction three, right? So what can lead to things like bubble, right? Where you have instruction one here, and you're not running anything here. What can lead to this? Data has that, yes. So basically, data, or sometimes we just call it data dependency. So if you look at the data hazard, what are the three types of data hazard? Read after write, right? So let's say you do add R0 from adding R1 and R2 together, subtract R3, R0 minus R2, right? So there's a dependency right here where I need to finish the first add instruction before the second subtract. If I give you a sample piece of code like this, you should be able to fill in a table to say what instruction is execute what. With pipelining, using stalling versus using data forwarding. The other two is write after write and write after read. What type of processor can run into write after write and write after read? What's the last topic we learned right before the midterm? So out of order execution can happen, right? Which means that you can have write after write and write after read data hazard. You do then use the reorder buffer as well as the or the renaming table to deal with it. Then we talk about the branch prediction, right? Branch prediction here. Why do we want to predict branches? Performance, yes. Let's say you have a code like this. We can say loop, right? And it merge back like this. If you do pipelining, which means that whenever you want to fetch something, you need to know the PC, right? When you branch, you basically set the PC, the value of the PC on branch. Which means that if you don't predict, you cannot really fetch. Right? You cannot really fetch until you know what's the PC value. So that's why we need to do branch prediction. We cover multiple types of branch predictor. We have the 1-bit prediction, 2 bits, right? And we have a 2-level predictor. So it's a totally fair game. If I give you a program, make some assumption, tell you those assumptions, and ask you similar to one of the in-class exercise on what's the accuracy of certain branches. So make sure you are aware of how to perform branch prediction. Any question about branch prediction that you want me to go over? Because otherwise, if you have not gone through the in-class exercise, definitely go through the in-class exercise. And there are 3 things you need to predict, basically 3 things. The first thing is the instruction a branch? The second thing is where do you branch to? And the last thing is we taking that branch So you need to answer all three questions to predict the branch. The next thing we learn is precise exception. What's the benefit of precise exception? Why do you need this? What is precise exception? Actually, I might have to go one step backward. What is precise exception? You're getting there. Actually, this is basically maintaining sequential semantics, right? Basically, you maintain the sequence of the code that you see on the assembly file, even though you do pipelining, even though you do out of order execution. When things like exception happens, you need to maintain that sequential semantic. The reason why I use the word semantic is means that even though you're not really running in sequence, you need to maintain the semantic that hey, I'm running it sequentially. I'm faking it by running different things in out of order execution. But if exception happen, you need to come back and maintain the sequential semantic. So the benefit of precise exception is to make sure that when you run code and exception happen, you can still go back and debug your code. If you have interrupt, you can resume correctly. And this is done by having this reorder buffer, right? The reorder buffer allow you to run your code in any order as long as the write back to register file is done in sequential order because that's what the programmer sees. So as long as we tell the programmer that's the order, you can do anything. There's so many things in hardware that as a programmer, you're not aware of what's happening. To get more performance, we love to do weird things in hardware, and the programmer should not realize that we are doing it right now. As long as the program is correct, as long as there's no random security flaw, you're good. You're good. You save power, your program runs faster. Execution. Sorry about the typo. Then we cover out of order execution. Any question about the out of order execution? Because my recommendation is unless we want to spend the next 30 minutes on the sample question I sent you, one good way to go through that is to go to that particular lecture video. It's the video right before the review session. So that's the Wednesday video, Wednesday last week. These basically imitate data flow even if the ISA is one Neumann. Why do we want to do this? Data flow is faster, and one Neumann is easier to program. So we get the best of both worlds. Software is done in one Neumann, hardware imitates data flow. We get performance, programmer life becomes simpler. All right, so that's the benefit of outer order execution. So what I think lecture lecture 10 video have a pretty long sample of how we can solve out of order execution and how does it go. Basically how you will go through that. Here is what we have during lecture 10. I already also post this files, so you can see this in on Canvas. And here's the solution for that particular question. We went through this in detail. For the interest of time, go watch the video. If you have any questions specific to this, you can ask now. Otherwise, before we leave today, one thing I want to make sure that you are aware of, sorry, is assignment two is out. It's out for a few days now. What we want you to do is pipeline with stalling. Remember, we have checkpoints, real checkpoint. This is 10% of your rate. And the checkpoint is basically uh, make sure I want to make sure you have a concept of how you want to split your design into multiple pipeline stages. You don't have to make it correct. I just want to see that the fetch, decode, execute, memory, and write back. And you have some idea about what fraction of the code should go into the fetch, what parts go into the decode, what parts go into the execute, and how do you break them together, basically break them apart. And then from the checkpoint, you can then talk about stalling. How do you stall? How do you detect data dependency? Where do you update the PC, which is the write back stage, right? Uh, Extra credit. If you do data forwarding, so the main assignment doesn't ask you to do data forwarding. If you do data forwarding, you get extra 50% of the 100 points, so you can get up to 150. This is especially true for those of you who kind of like, hey, I did not finish assignment one. This is how you can recover and how you can catch up. I hope this is a good enough motivation. Especially if you did not submit assignment one, this is your second win, so that you don't get overly penalized, even though you did not finish assignment. And for those who want to try data forwarding, then you get 50% of your grade on top of it, right? So it's a lot of points. It means that you can manage your time in the future. And if you somehow get this correctly, is a lot of points to your grade, right? So okay, that's a good motivation to do something harder from the assignments. It's not that hard. Because what I can tell you is this is the lab that I have to do in the hardware description language as an undergraduate at CMU. This in here you do this in C, that already makes things a lot easier. And I have to do data forwarding. It's not extra it's not the extra credit. I have to do that in 2 weeks. So I know it's totally doable, especially if you're dealing with C code and you have 4 weeks on it. I'm giving you 4 weeks. That's all for the assignment. Let us take a quick break before we come back to a sample exam in case you had a chance to went through this. So that if you have question, I can address. All right, so let's meet back at 10:15. I don't know why I think it's 10 o'clock. At 1:15. All right, so let's meet back at 1:15. Then we do a Q&A. And this, again, is driven by you. We will go through the sample questions. I'm gonna keep sharing that screen so you can take a look at, hey, this is the sample things that you can have. Maybe I'll just put it on this slide. Prediction. Let me save the slides. What's that? Yep. Okay, so let's meet in 10 minutes. All right. All right, let me know if you're back. For some reason, WebEx doesn't allow me to. I can't access it. Okay. All right. So, any of you have any questions on the sample that we have over here that I show? Any questions that you want me to go over now that we are back? Because otherwise, I'm gonna let you look through the questions, especially basically the question 1 to 5. Question 1 through 5. If you have any questions from those question 1 through 5, let me know so we can go through them in the during the rest of the time. Basically, don't worry about the question. Okay, 3B, sure. So if we go to question 3, which is the in class exercise, here, notice how I have the correction over here from the announcement. Basically, that's supposed to be A000. In here, I'm gonna write, wait, how do I write it from? Oh, so I'm trying to figure out how do I use the monitor that you share this to you at the same time. Let me unshare my monitor and share another screen. Give me 10 seconds. All right, can you see the screen with just a blank, a bunch of instructions you can put in? Okay, so the first thing you do is copy over the bits. Copy over the bits. From here, I said my instructions start at 0x a0, right? So that basically becomes a drop 8 0 0 0 followed by 8 a 0 0 followed by 8c14 followed by f e f f followed by 7214 and 0a6e and what and then E1BA, and then 9140, and followed by A000. And this is basically jump 0, which terminate the program. Right. The rest we'll do one at a time. This is 1 0 0 0 0 0 0 0 0. This is 1 0 0 0 1 0 1 0. This is 1 0 0 0. C is 1 1 0 0 0 0 1 0 1 0 0. This is 1 1 1 1 1 1 1 0 1 and 1 1 0 1 1 1 0 0 1 0 0 0 1 0 1 0 0 0 0 0 1 0 1 0 0 1 1 0 1 0 1 1 0 0 0 1 0 0 1 0. My bad. Did the conversion wrong, so let me erase it. This is 1 0 1 1 1 0 1 0. That's 9 1 4 0. So that's essentially 1 0 0 1 0 0 0 1 0 1 0 0, and the last number is 0 0 0. All right. Okay. So from this number, you notice that this one is basically LDI 0 0. This is LDI again. If you basically you go and map from here, you look at the bit pattern that correspond to what you see here. Then this is LDI 5 0, right? This is 5, the rest are 0, and this is load, right? The next one is LDI. This is 6, right? This 3-bit is 6, so this is R6. What is this number? Oh, what is 16 plus 4? 20, right? Or 0x14 in hex, basically either format would work. LDPC R7 load R1 R0 20. Okay. And then add R5, R1 and R5. R5, yep. R5, R1 into R5. And then the next one is add immediate. Because if you look at this bit pattern, that's add immediate. Our immediate is 2, and our register is 0. Okay, so it is add immediate R0, 2. Go back up a little bit. Add immediate here, source and destination, right? And destination here is 0. 0, 2. What else? So the next one is branch not equal. R0, R6, and R7. So basically, if R6 and R7 are not equal, you branch. Otherwise, you then store R0, R5, and 0, and then you done here. So that's the solution to 3B. First, go through the bits, then from the bits pattern, translate it to each instruction based on the table that we see up here. I'm faster because, well, I have the solution on the other window, so I'm cheating. The part I convert from the bit to instruction, I'm kind of, well, I know the solution. So that's the solution. I just need to double check that is correctly mapped, but I did that check once already. And then the program basically it kind of like sum every other value. So you skip odd addresses, you go even addresses, and start from address 14 to address 26. And then in total there are 9 summation if I got the number correctly. Then it would write the results to another address. Over here, not expecting you to do this state of the memory. Oh yes, yep. That was the typo on the question. So these things supposed to be, yeah, basically this is supposed to terminate your program. So this is A000. My bad. I'm so sorry about that. Yeah. So if you can find jump 0, which is now with the correction, you should be able to just, it should end within these many instructions. I think 7 or 8 instructions. All right. So maybe let me go through this version. And let's quickly do machine A. So let's just go through this branch prediction question. Over here, I start with the assumption. So read the question carefully for the branch prediction question because I'm going to state a bunch of assumptions. Over here, one number of assumptions is taken means that we go in here. That means I take the branch. The second thing I want you to realize that three machines, right? Each machine use different branch predictor. Let's do machine C. Let's do machine C. Basically, what's the accuracy of machine C? And then I specify the saturating counter. This is the same. Basically, this is exactly the same as how we do it in the class. And so this is question A is for machine A, question B is for machine B. Machine A is always going to take the branch, so you should be able to do that. The answer to question A is basically 226 over 5,000. Don't forget the exit for loop. For question B, the answer, let me give you the answer. So there are three parts when I is between 0 to 249, when I is 260 to 499, and then when I is 500 to 1000. This has 375 miss prediction over 12050 branch. This has 874 over 12050. And this has 1750 over 250. So in total, you're gonna get 59.97% miss prediction. And here is machine C. Machine C is a little bit easier actually. So basically you do branch 1, branch 2, branch 3, branch 4, and branch 5 separately. So you go back to our branch here, right? Branch 1, what's the, so here, what's the pattern for branch 1? What's the pattern for branch 1? It's always going to be taken. To the last one, which is not taken, right? It's a loop. So you take it all the time until you exit the loop. Branch 2, what's the pattern from branch 2? I just check if I want 2 loops with 0. The first time I hit 0, so that's it. This is going to be followed by nothing. Oh, my mic work. Can you hear me? All right, perfect. Yay. So I was asking what is the pattern for each of these branches? And for the first branch, it's a loop. So it's going to be taken, you take the branch until the last one when you exit. The second one is simple. It's I modulo 2. So it's going to be taken, taken. The third one is going to be a bunch of taken, followed by a lot of not taken. Same things go here. Taken, followed by not taken. There'll be 250 of the taken, 750 of the not taken. Over here, this going to be 500 and 500, right? And for the last one, it's going to be 500 not taken, and then 500 taken. So our local predictor, basically we can do it broken down by branch, right? For B1, is mispredict at I equals 0 initially, right? Otherwise, afterward, it will start predict correctly. So at I is 1, correct? And then mispredict again at I equal 1000 because that's when you exit the loop. Over here, this is going to be problematic because if you just look at B2, if you just look at B2, this mispredict all the time because this is oscillating between weekly taken and weekly not taken. This branch over here will be mispredicting at I equal 0, I equal to 50 and 251. Why is that the case? Initially, you are taking the branch, right? So you start from uh, predicting not taken, but in reality, you are actually doing taken. Then you switch over to taken. You're gonna predict that hey, you're gonna take the branch. It's going to the strongly taken. So when you are from strongly taken, it takes two branches to go to weekly not taken. And when you add weekly not taken, 250 and 251 will shift you back to strongly taken to weekly not taken, and then you get the rest are correct prediction. This thing has the same pattern, but now it's at I equal 0, I equal 500 and 501. Over here, when I is 0, you add weekly not taken, so you're correct. So the only time you're incorrect is at I equal 500 and 501. So in total, this misdirection rate is 10, 1010 over 5001 branches. 2 over here, 1000 over here, 3 over here, 3 over here, and 2 over here. So this is where it gets 10, 10, 10. 2 plus 2 plus 3 plus 3 plus 3 plus 1000. This is 1. So, so let me recap again. This is we use local, which means that you use PC value. You don't have the two level. There's no local history register because we haven't tell you that it's one level, but each PC has its own separating context. So that's why you just break it down by different. Machine B is a little bit more complicated because now you have the THR. So the THR would dictate the pattern, and then you go from there. I would definitely recommend you to go over part A and part B so that you get some practice with the THR. And then part D is essentially what if I switch the initial condition of my saturating function? And with part D, the result is basically 10-16% misprediction. All right, so that's for the branch prediction question. We covered this already. Let me quickly go to. Don't worry about this. I'm not going to ask you something along this line, but it's a good practice if you want to try. If you have questions on that, let me know. We covered this part already, actually. Let's do this. Let's do this third one. Which one is the microarchitecture and which one is the ISA? What about the number of adders? Are those microarchitecture or the ISA? All right. Who else? What's your guess? It's actually microarchitecture because if you look at the ISA, it doesn't tell you how many adders there are. If I have more adders, the hardware implement those adders, and the hardware implement how do you put the instruction to those adders. Oh yeah, it's the adder, not address. My bad. How about the vector interrupt? Is that the ISA or microarchitecture? Vector interrupts are, so if you remember from File Pro, vector interrupts are those jump table that handle the case where you have interrupts, things like you tap on the keyboard or the mouse move, things like that. There's a table that I was about to say that the ISA specify what to do and how to handle it. Yeah, so the answer is the ISA. Number of entries in the reservation station. Is that the ISA or is that the microarchitecture? It's actually the microarchitecture. It don't tell you even so. Let me put it this way: when you program and look at the spec sheet of the ISA, it doesn't even tell you that they're doing out of order execution. Reservation station is a part of out of order execution. It's how you implement the hardware. So how about the entries in the future file? So this is like the reorder buffer plus plus, or like a better way to implement the reorder buffer. So we didn't cover this in class. This is more like a graduate level material about like, okay, if we learn about this structure, how can we make it more efficient? It's microarchitecture. How about the number of entries in the architectural register file? Number of entries inside your register file. That's the ISA. Okay. The existence, so we haven't covered the load stock queue. I'll tell you it's an architecture. Basically, this handles how many load and store requests you can have in flight at the same time. The program counter, we had that already, so that's the ISA. This is actually a good thought question. Why does the ISA change more slowly compared to a microarchitecture? Anyone want to take a stab? So one of the answer that you are giving me is changing the ISA doesn't result in better performance. That's false. It can impact performance. Let me put it this way. How about we as a human come up with a new language every year, and then the next 2 years you need to pick the new language to use. It's actually not too hard to come up with one too. You look at that table we have in exercise, the question 3, right? I came up with that ISA within about a few hours. Actually, in fact, I came up with that within like 20 minutes, and I make sure those are Turing complete within a few hours. It 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 means that whenever you change the ISA, you need to change every single piece of software that want to run the new ISA. Every single piece of software suddenly have to speak that language, right? So that is problematic. It means that the compiler have to change. It means that the programmer have to change the way they program. Adopting a new ISA is hard. Adopting a new ISA is hard. So you better not change it all the time. Adopting a new CPU is not hard. whenever you have a new generation of CPU, for example, Intel, right? Current generation of Intel processor versus previous generation of Intel processor, they perform better. Those are microarchitectural changes. Do you have to modify anything in your program to use the new chip? Do you have to modify anything inside your program? No, right? It's actually backward compatible. So think of it this way. That's why changes in hardware on the microarchitectural level happen a lot more frequently. And sometimes we just introduce new instruction to the ISA. It's kind of like you keep using English or Thai, but we have new words, right? We have new words inside the dictionary. We define new words that mean some unique thing that appears that is more convenient to come up with a new word. Does it kind of clarify why you should care about either of those, like the ISA or the microarchitecture? Think that's pretty much what I would like to cover today. Any last minute questions that you want to ask? Let me save this to make sure that I can post it for you guys. So I'm gonna post this notes that I put in on the PDF into Canvas so that you can take a look at some of the markings that I have. Any questions before we call it a day, and feel free to check back with me on any kind of email or message that you can contact me if you have last minute questions related to the material we covered so far for the exam.